Hello, physics. How we doing? Mr. Walters here. We are continuing our discussion of the electromagnetic spectrum and how it relates to the universe. We're going to be talking about what the universe is composed of. You're going to hear terms like dark matter. You're going to hear dark energy. Sounds very ominous and mysterious. We also are going to talk about the Doppler effect, what that is and how it's used. And in fact, the Doppler effect is used, the data, understanding the Doppler effect has led to this, given great credence to the evidence that yes, that the universe that we are a part of is expanding. Anyway, I wanted to review a little bit of the emission spectra of light of various elements. This is how scientists, astronomers can analyze light, and they can, when they analyze the light, they can develop fingerprints of the different elements of which the light is being emitted. So you could think of these emission spectrum as elemental fingerprints. Just like your fingerprint is unique to you, sodium, potassium, iron, neon, helium, hydrogen, when they emit light, when they're energized, heated up and start emitting light, that light can be analyzed, and we can essentially from that spectra determine what element is present in that heated up material. So, as I alluded to in the previous video, if you've ever wondered how do they know the sun is composed of hydrogen, helium, boron, carbon, quite a few other elements as well, well, they simply analyze the light that's being released from the sun, and notice as we send the light through this prism, we're going to separate the white light into its component colors. And we're going to analyze the white light, and when we analyze the white light, there's going to be characteristic bands which are unique for different substances. So here we have characteristic bands for iron, characteristic bands for sodium, characteristic bands for lithium, carbon, sulfur. In fact, it is these stars that are the furnaces which forge the elements of which all matter is composed of. Boy, I wish I had written that down. So, any of the elements on the periodic table, any and all, with, I guess we have to say, some exceptions towards the very end of the periodic table, which are man-made elements, which is a whole nother story. But any of the naturally occurring elements were produced by stars or exploding stars. And those exploding stars, they release these elements, like iron, for example. They release that out into the universe. Eventually, the matter begins to coalesce. And as more matter coalesces, we can start producing suns. The force of gravity begins to take over and keep that mass together. In a similar way, other materials will come together and begin circling the sun due to the sun's gravitational force, and matter will coalesce, and planets are going to be produced. In fact, since all of matter is made from stars and exploding stars, essentially the heavier elements, if you go beyond iron, those need greater temperatures and pressures, so that's where exploding stars called supernova will, nova and or supernova can actually produce the heavier elements that go beyond iron. Anyway, it's interesting and a little bit poetic to think about that all the matter that composes your body has come from an exploding star. So the iron that is now part of your hemoglobin, part of your red blood cell, an individual red blood cell has an iron double positive ion present. And that's really important because that's going to grab oxygen and transport the oxygen in the bloodstream. But that iron atom and all the iron atoms in your blood right now, all the atoms period in your body right now have in fact come from stars and exploding stars. In a very real sense, this sounds poetic, and it is poetic, but it's also literally true that you and I, all living creatures, are made of stardust. Something to think about. Anyway, notice we're going to analyze the light produced by this galaxy here. And notice we're going to get these spectral fingerprints. And again, we can determine the different elements that are present in the source material that's emitting this light here. Maybe just to review, there's our white light, which is now, once you separate the white light into the component colors. School has started. I'm glad you got here early. But notice we could just review a little bit of the electromagnetic spectrum, and here we have Roy, G, Biv. So red, orange, yellow, green, blue, indigo, and violet. On the red side, we have a long wavelengths. We have low energy. On the blue side, we have shorter wavelengths. The blue and violet side, we have shorter wavelengths, higher energy. If we get shorter than violet light, we'll go into the ultraviolet spectrum. Then we'll move into X-rays, and then these tremendously dangerous cosmic rays. If we move from red light and get longer and longer, we'll eventually move to microwaves. We'll move to radio waves eventually as we get longer and longer wavelengths. I do want to do calculations which concern wavelength, frequency, etc., but we're not going to do that right at this moment. So let's move on. Notice, as we have a car that's releasing sound waves, notice as the car's approaching you, so let's say you're over here. This car is releasing sound waves, but the source of the sound waves is coming at you. Notice, for this person here, not only is this person going to get hit by the car if he doesn't move, so I better get out of the way, but the sound of the approaching vehicle is going to appear to have shorter wavelengths. That's going to be, it's a relative thing. It's relative to this observer here, that the sound will appear to have shorter wavelengths and will have a different sound as that car approaches. Notice, as the source approaches, we get a shortening of wavelengths. Conversely, this car moving in this direction, away from our Nobel Prize winner here, notice the wavelengths will be stretched because the source is moving away. So pay attention when you hear a motorcycle go by. You're going to get a different sound as the motorcycle approaches you from a different sound as the motorcycle goes by you. This is called the Doppler effect. And this is fundamental in physics and also in astronomy. Again, so here's our car leaving. Notice the wavelengths. The wavelengths stretch out when the source is going away from the stationary observer. Now, we also talked about the effect of light and what happens to the luminosity of light as the light source gets farther and farther away. Notice the light gets dimmer and dimmer and dimmer as the distance recedes into the deep background. Is there a mathematical relationship between the luminosity of the light and the distance away from the observer? There certainly is. So you need to go ahead and get this. So we are measuring distances with a standard light bulb, meaning the standard light source is the same. So this is this light bulb here has the same brightness as this. So that's what we mean by standard light bulb. Notice, as an object becomes fainter by the square of its distance. So go ahead and get that. So notice, here we are. Let's say we have the luminosity here is going to be 4 at this distance. Notice, if the distance is doubled, we have the luminosity here changing not by a factor of 2, but by a factor of 4. We could look at it the other way. We could say, okay, let's measure the luminosity of this bulb here at a distance of at this particular distance. Let's move the bulb from let's say 20 yards here to 10 yards here. So notice we've gone from 20 to 10, so we're getting closer. You'd expect the luminosity to go up, but the luminosity goes up by a factor that is the square. What do you think would happen if we go from 20 to 10? Then if we go to 5 right here, by what factor would that go up? It wouldn't go up to a factor of 8, it would go up to a factor of what? So that would be a factor of 16. Anyway, this is important for astronomers in measuring. And go ahead and make a note. This is one of the ways that Hubble made his calculations. So we're going to see that Hubble uses the brightest stars to measure distances to the nearest galaxies. He assumes that the brightest stars are all the same brightness. And what he concluded is something really important. You don't get orbiting space telescopes named after you for being a dummy. So this is pretty important in terms of understanding what's happening in our universe. The faster the galaxy was moving, the fainter the stars. And there's Mr. Hubble. Incidentally, Mr. Hubble was supposedly not only a great mind, but did everything well. Great athlete, college athlete. Played several different sports, if I'm not mistaken. It's been a while since I've read about him, but he was genuinely talented in a lot of areas. And you don't have to write this, but this is just plotting some of Hubble's data. From Hubble's data, it was determined that yes, and put a big exclamation point, the universe is expanding. So this is good work done by him, which occurred quite a long time ago. Okay, just making sure I was still recording there. Didn't run out of something, juice or whatever. So yes, the universe is expanding throughout the next couple days. You're going to hear about a couple different concepts again throughout the next couple days. But the space can be, space is curved. Space is curved, and this is Einstein. So I've mentioned it before in class that you could think of space as a kind of a soft velvet, black velvet tapestry that when you put an object on that soft, stretched out velvet, that object will weigh the velvet down and curve the velvet. It's this curved space that is responsible for gravitational force. And this is Einstein in his general theory of relativity. It's Einstein and Newton, the two important people that did a lot of their work with gravity. Since space is curved, objects which get near that curved space will be attracted. So that's the gravitational force. Space has more than just 3 dimensions. Space has 4 dimensions. Typically you think of length, depth, and width. Now though, this is Einstein, and this is Fact Jack. This is a Fact Jack. It has the 4th dimension of time. So when you hear space-time, 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 that is what space is made of. It's 4 dimensions: length, width, depth, and time. One of the reasons Einstein became famous, actually, this is just one of the reasons. He did work in a lot of several different areas which were really, really important. But according to his theory of curved space, he predicted that massive objects would not only attract other objects which have mass. For example, the sun is a massive object. Of course, it attracts the planets. He predicted that that curved space would also change the direction of light. So light traveling by a massive object will also get bent or curved. He made that prediction, and this is science at its best. Science comes up with hypotheses, evidence for theories, and then makes predictions. Do the models, do the present day models make accurate predictions? That's what science is all about. You come up with models. If they can't predict anything accurately about how the world works, you have to scrap that model and come up with a better model which incorporates which incorporates data which actually does have some predictive qualities. So anyway, Einstein predicted that that because of space-time curvature, light would be influenced by the massive object of the gravitational force. Again, it has to do with that curved space-time. Well, sure enough, he made the prediction. Maybe 10 years later, this prediction was verified. Essentially, what happened, there was a total eclipse of the sun, and some astronomers took pictures of light that was beyond the sun's, essentially behind the sun. Those light rays passed to the astronomer by the sun. There was a total eclipse there, so now we can take pictures. And it was determined that yes, in fact, the light waves were bent as they passed by the sun. Einstein predicted they were going to be bent to a certain degree. I forget what it was, maybe 1.7 degrees, something like that. And he was accurate to a significant digit of maybe plus or minus 0.1. Again, don't quote me on that, but it was phenomenal. Anyway, so notice here, the expanding universe. If we are observing something from this point, and if we're observing a star that's close by, it takes some time for that light to actually make it to the observer here. But if we're observing something that's distant, many light years, notice it simply takes time for the light to move. By the time it reaches this observer, let's say that a million years has gone by. So this observer is seeing something that happened a million years ago from this light source or this star. This, on the other hand, might have been 25 years ago. My point here is that when stars are being analyzed, when distant stars are being analyzed, the more distant they are, the more we are in fact looking into the past. And this is why that Deep Space Hubble image is just so interesting to me personally, is because you're seeing what happened 12 billion years ago. 13 billion years ago. It took that long for the light to finally reach the Hubble Space Telescope for us to take a picture and for you guys and me to check it out. Take good notes. It's important. You're not just taking what's here. My whole discussion should not be, I shouldn't see on your notes that this whole discussion was this picture and this, and then this guy. So notice, we talked about the Doppler effect. And when an object is moving away from you, the wavelengths stretch out. So notice, as we are accelerating away from you, notice these waves stretch out. And you guys remember Roy G. Biv, violet are short wavelengths, red are longer wavelengths. So when a light source, visible light, you know, the light emitted from stars, if the stars or the galaxies are moving away from you, we get what's called the red shift. We shift towards the red area of the spectrum. Of course, if an object that's emitting light is moving towards you, accelerating towards you in the other direction, the effect is the opposite. You'd have a blue or violet shift. So I want you to understand this concept as it relates to the electromagnetic spectrum.